Hello and welcome to Lab Down Under. Today I'll be talking with Dr. David Murphy from the Queensland University of Technology about his research on ancient volcanic rocks and what they can tell us about geological processes that happened on the Earth about 3 billion years ago. It was all a very interesting discussion that I had with him about exactly what these rocks showed us about the world back then and what life was like on a very, very different Earth than it is today. So please, let's get on with the interview, and I hope you enjoy it. Welcome, Dr. David Murphy.
Thanks very much.
Yeah, no worries. Thanks for taking the time to speak to Lab Down Under today. Yes, and as mentioned, you did a recent study on ancient volcanic rocks and basically what that could tell us about the geological processes thousands of millions of years ago. Is that an accurate summary of what the research was?
Yes, so essentially certain areas in the Earth you can find preserved volcanic rocks that are in very good condition, considering how old they are, and you can investigate both their mineralogy and their chemistry and then use that to infer the types of processes that occurred early in Earth's history, and then from that start to begin to understand the nature of the geodynamics, how the planet was actually behaving billions and billions of years ago.
Mm-hmm. Okay, so I've got the name, the actual name of the paper here. How do I pronounce this? Paleoarchean?
That's correct.
Paleoarchean, yes. So Paleoarchean very old-bearing metabasalts from the East Pilbara terrain formed by a hydrous fluid phase exsolution and implications for Archean greenstone belt magnetic properties. There's a lot going on in that title, so
yes, it is.
Simple terms explain what that.
Well, let's go through it systematically. So the Paleoarchean is a particular time period in the Earth's history. It goes from, just to be correct, I'll just look over here, from about 3.6 to 3.2 billion years ago, and so it's not long. Well, they're among the oldest rocks that you can find on the planet. There are other rocks that range in age from about 4 billion to 3.6 billion, which is the Eoarchean period. And then before that in Earth's history, so for the first 500 million years of Earth's history, essentially, the rock, whatever geodynamic processes that occurred at that time destroyed all rocks older than about 4 billion years. There are a few possible rocks that might be around 4 billion or slightly older, but almost everything that existed on the Earth before that has been removed by basically cycling and mixing and due to the geodynamic conditions that occurred at that time. So we're looking at rocks that effectively formed in a certain geometry such that the whole crust that they form part of over in the Pilbara in West Australia, and they have remained relatively undeformed, unmetamorphosed for most of Earth's subsequent history. Effectively, that means that you can go to these areas and find examples of rock types that give you a really good indication of the types of conditions that were at the planet at that time. So, like, in addition to, say, the volcanic rocks that are present in the Pilbara and other places like in South Africa and the Cap Val Craton, and other people go to North America, various places around the world where you preserve these old rocks, you can occasionally go and find these well-preserved examples. It includes basically the sedimentary rocks that contain the evidence of the oldest life on Earth as well, but the vast majority of rocks that were actually occurring at the Earth's surface at that time were volcanic rocks. And that is essentially because at that time in Earth's history, there was very, very little evidence of land. There was very little indications that, say, any continent or continental material that were present at that time were actually above the ocean. So everything was essentially submarine. It would have been, I think, what's the film that they go to is it Interstellar? I think it is. And they go to an
yes, the
world.
one that's completely covered in water.
Yeah. So the very early history of the Earth and would have looked very similar to that, with very little small islands sticking out of the ocean potentially. So it really does imply that there was a very different conditions at that time. So then the next part of the title is that these are vario-bearing pillow basalts. So a pillow basalt is a volcanic rock that erupts under the ocean.
Okay.
So you can see right now in the present day, the Iceland erupting, Etna is also erupting. These are all subaerial eruptions, and you can see the lava flows percolating out along the ocean, or sorry, along the surface of the Earth. People are able to go and check them out. So this volcanism that we're looking at in the Archean would not that dissimilar to what's occurring in Iceland at the moment. It's still the Iceland volcanism. It's coming from 20 kilometers down in the Earth's mantle and transferring through the Earth's crust, or the Icelandic crust, and then coming out at the surface. It's not that dissimilar to what we would have seen here, except that this was a submarine volcanism. Now, there's also most of the Earth's present-day volcanism is also submarine, because most of the volcanism that occurs in the Earth today occurs in the middle of the ocean. So the ocean.
Yeah.
Sorry?
I was going to ask you about that, because most of the kind of headline volcanoes that we see, they're all above, like you said, Etna,
yes.
Yeah, Iceland, New Zealand, they're all like above the ocean. But we're aware of many. You just said most of them are found.
But the vast majority of volcanism is submarine.
Yeah.
So even today, like you can go to the beaches around East Australia, and you can find pumice. That pumice is a volcanism that's not that different to the style of volcanism that's occurring in the Caribbean right now. But if it erupts underwater, then all the gas that's causing that explosive activity forms basically a pumice rock, which is a very bubble-rich material. So and then it's so rich in bubbles, essentially, that it becomes lighter than water and can actually float. So, but even more so in the center of the oceans, in what's called the mid-ocean ridges, there's like these volcanic mountain ranges that's really clear and obvious in places like down the center of the Atlantic and through the Indian Ocean, and then it's kind of stepped over towards the U.S. coast in the Pacific. But these are areas where the Earth's crust is essentially being pulled apart, and as it's pulling apart, you're getting basaltic magmatism occurring as well. And in those scenarios, because this is they may be elevated relative to the surrounding oceanic floor, but there's still 2,000, 3,000 meter depth. And in those scenarios, you also get these pillow lavas. And it's like the lava it's almost like it squirts out of the vents, and it's a bit like toothpaste coming out of a toothpaste tube. And so it forms those kind of like, it forms long, elongate strings almost. But when you see them commonly, you'll see them cut across at right angles, and then they kind of look like stacks of pillows. So it's just a descriptive term for that. So the morphology of these pillow basalts in the Archean indicates that they erupted in a deep water, well, certainly in water conditions. Then you've got this other feature within these, which is varioles, which are very uncommon. They're actually I can find one example of one from the present day mid-ocean ridges in the literature. So they're very, very uncommon feature in the modern day basaltic magmatism, but they're actually quite abundant in the Archean equivalent. So it suggests that the process of formation of these pillow lavas between the Archean and the present day, that there was a significant difference. And effectively, if I'll just pick this up, I'll bring it in close to the camera. You can see these features, the circular features that are present in this rock. So this is one of the rocks that was analysed in the study, and we basically hypothesized that these formed instead of bubbles in the lava. So in the present, like again, going back to the Icelandic example, you can see in present day eruptions, you can see gas being exhaled off the lava. It's a health hazard. There's so much sulfur dioxide coming off it that all the people that are going to check out the eruptions are warned about the poor air quality, because there's both sulfur dioxide, carbon dioxide, probably carbon monoxide, water vapor, all that was dissolved in the magma when it was under pressure, and then when it comes up to the Earth's surface, a bit like opening a can, carbonated drink or so, and then it suddenly gets released. And that's why when you look at the lava that's coming out of somewhere like the Icelandic eruptions, the very upper surface is very, very bubbly. It's almost like pumice as well. It's not quite as low density as pumice, but still very, very what we call vesiculated, which means full of bubbles. That also occurs in, again, if you go into, you can there's videos on YouTube of submarine submersibles going down and actually viewing pillow lavas. You can even, it's actually, they go and they die when in Hawaii, when the volcanism is entering the ocean, people will actually dive into where the ocean is, where the lava is going into the ocean, and they can film these pillow lavas forming. So in that case, when you can see such things happening in Hawaii, in the mid-ocean ridges when they send the submersibles down, and most of the time, those same volatiles that we see bubbling off the lava in Iceland today form again bubbles in the outside of the pillow lavas. What's very interesting for these pillow lavas is that we see very, very little bubble formation around the edges of the pillows, but we see these feature instead present in it, the varios. Now, this is very much a working hypothesis, and it needs a lot of, probably some significant experimental work to really verify this. But we've hypothesized essentially that these pillow lavas are erupting in water that is super, super deep water, and that's actually suppressing the degassing of the magma. So instead of the volatiles, the water, the CO2, etc., that are present in the magma exsolving as a gas phase, we're actually hypothesizing that at this higher pressure, which means very deep water, that these volatiles are forming a liquid inside the basalt, and then you have essentially chemical exchange between that hydrous fluid and the silicate magma, and it forms this texture. That is our hypothesis, but it really needs to be experimentally verified to really assess if this is viable. But if we could actually verify it, if we could experimentally test this model, it would then potentially allow us to say how deep the water was.
Right, okay, of course, because you need
quite a cool thing to be able to say. It's like you can basically say, oh, we have these, suggest deep water, but we don't really know how deep that water would be. So in the ideal case, we'd like to do actual physical experiments where we make a magma and then put it under pressure and then see if this phenomenon actually occurs in a laboratory setting, and then be able to use those numbers to basically say how deep the ocean would have been in that time period.
Oh, that's awesome. The process that you've worked out in the title, you've got the phrase here, hydrous fluid phase exsolution.
Yeah.
Is that's basically what you were talking about then with
Exactly.
the...
So
Yeah.
instead of basically, so a hydrous fluid phase in that case is like probably a supercritical hydrous fluid, rather than what you see in the Iceland now, which is what water that's dissolved in the magma just directly turns into steam and evaporates as a gas or exits out of gas. So it's that subtle difference between basically a fluid and a gas, essentially, in what happens to the volatiles. So
Okay.
I'm not really allowed, if it's correct, and it is very much a hypothesis at this point in time, then you can use these observation of these types of lavas to effectively make inferences about water depth, but also environment, but even environmental change. Because what's quite interesting is that there are other rock types that are occurring in the same stratigraphy, so occurring roughly in the same time. It's very hard to get time, like basically when we're attempting to get an estimate of how old these things, we're looking at plus or minus 5 to 10, even to 20 million years. So, so these are, because you're looking at, well, 3.5 billion year old rock, then you're looking at an error of, you'll be really happy with a, well, even less than percent level or variation on that. So there's quite a, it's very hard to get an appreciation of timing or absolute timing of events. So what's quite interesting here is that these are actually overlain by rocks that include stromatolites. So do you know what a stromatolite is?
No.
So stromatolites occur in the present day in West Australia in Sharks Bay. And essentially stromatolites are interpreted to be algal mats that form in shallow water where the algae is actually photosynthesizing. So so these are the unit that overlies this, which is a Duffer formation. It contains these stromatolitic components. So then it may not have been what we consider to be a, blue-green algae right now, but a precursor to that was potentially photosynthesizing. But what that indicates is that in the time period from when the variole-bearing rocks were erupted to when the stromatolites formed, it went from very deep ocean environment to a very shallow environment. So that suggests essentially that the sea level, not necessarily the sea level, but the sea level is probably staying the same, but the land surface is basically moving up and down in time, and potentially on quite a short time frame. Short in Archean or geological terms, like less than 10 million years to potentially go from maybe kilometers deep in the ocean to however deep it is to photosynthesize. So only like less than 100 meters or so. So, so there's really cool implications in terms of the dynamic nature of the Earth's surface at that time period.
The main, I guess, finding of the study was then this hypothesis of how these rocks formed all those billions of years ago, right? Or was there anything else to it?
So, and the major, well, there's a lot of sort of implications from these. Like the texture alone has a very interesting implication in terms of the depth of the water. But another thing that's very interesting in there is that these rocks are providing evidence that the magma had a high water content and a high CO2 content, which is a little. So this really comes down to an appreciation or an understanding of the sort of the geodynamics, the nature of the formation of the Earth's crust at the time in Earth's history, which is really quite challenging to reconstruct because there's so few places with well-preserved examples of rocks of this age. So we're trying to basically global effort of many different places around the world where you do find these rare occurrences of ancient rocks to try and piece together how the Earth worked at that time period. Well, we got a very good understanding of the present day Earth. You've probably heard of the plate tectonic theory, which is where the continents are moving relative to each other. Australia is currently moving northwards at a few millimeters per year. So eventually it'll crash into Papua New Guinea and then Southeast Asia, many millions of years' time. Similarly, India has originally started in the southern parts of what would consider the present-day Indian Ocean, has moved northwards and crashed into Eurasia to form the Himalayan mountain belts. So that's the plate tectonic process that's occurring today, and most volcanism in the present day is associated directly with that motion of the plates. Interestingly, the time period these rocks formed, there's no clear indication of whether rocks were, whether there was plate motion and whether these rocks were associated with the movement of plates. And most of well, it's a big debate in the literature. Is there evidence of plate motion in the Earth's, in this time period? Or was everything kind of like stagnant and not moving relative to each other? These rocks, effectively, the fact that they're water rich means that water, presumably from the Earth's surface, had to get into the melting area where the melting actually occurred, which is in the upper mantle, so probably 50 to 60 to 100 kilometers deep at that time. So water had to get to that depth to actually, so presumably from the Earth's surface, and that's the obvious place considering it was a water planet at the time, had to get into that melting environment to then be incorporated into the magmas and then get to the Earth's back to the Earth's surface essentially. So that type of process occurs presently in many of the volcanic environments around the planet today, associated with plate tectonics, where oceanic crust is essentially, so you've got one plate here and another plate's diving down, and it drags water with it, and in the environment above or between the two plates, you have water released and it causes melting. So so our rocks could potentially suggest that something process like that was occurring. I'm not entirely convinced that that it's a modern style plate tectonic, but rather some essentially a slightly different, less plate tectonic like process that has brought water from the Earth's surface into the melting environment where these are coming from. So it's currently, I don't think it's obvious of the exact geodynamic setting that these things will have formed in, but it's adding to the picture of our understanding of the environments at this time that allows us to then start building models and start thinking about why such rocks occur, and why other rocks that are nearby. So I'm just about to finish another publication on rocks that don't have this water signature at all, that are that outcrop a couple of 100 meters away from these, and are part of the same unit. So we have different, essentially magma generation processes occurring at the same time in these same areas. So, and it all basically is starting to provide more and more evidence for the nature of the environment that was occurring at that time period, and then these observations can then be built into, say, numerical models, computer modeling, essentially of the Earth at that time period to then start making more predictions about what we should see in the field. So there's a feedback between field observations, the observations in the mineralogy and the chemistry of the rocks, feeding into the numerical models, and then a backtrack producing hypotheses to test that we go out into the field.
And finally, if my readers wanted to follow your research anywhere online, are you active on social media? Do you have?
I'm not the most active social media person, I have to admit. I do have a Twitter handle, but I don't actually post on it very much.
That's all right.
It's something that I should probably learn how to do, but I do have a Twitter post, but it's like there's very few posts on there. Probably the other location would be something like ResearchGate, which is a useful research related website that I think most people can access. So I can send you a link for that as well.
Yeah, that'd be good. Does your lab at QUT, does that have any?
Not as of yet a bespoke one. So it's just a school essentially that I need to actually do. It's another thing that's on the list.
Yes.
There's always lists.
All right. There's a lot of things. That list always seems to grow, right?
Yes. Indeed.
Okie doke. All right. Well, yeah, I think that does it for today. Yeah, thanks very much, David, for this.
No worries.
It's been really, really interesting. Well, I hope you enjoyed that interview. If you would like to learn more about Dr. Murphy's research, I will put a link to the Lab Down Under blog article that I've written on this below, and also we'll put links to Dr. Murphy's various university web pages, social media links, and such below as well. And as always, if you would like to support Lab Down Under, there are plenty of ways that you can do that. Following it on Facebook, Twitter, Reddit, YouTube, of course, LinkedIn as well. And I will link all of that below. If you would like to leave a comment, like the video, please don't forget to subscribe and click the little bell icon too. And we also have a Patreon page where you can throw some financial support to Lab Down Under as well, if you would like to help us continue to write about these hidden scientific discoveries coming out of Australia that really, really should have the spotlight put on them more. So until next time, please keep on being curious, and I'll catch you around.